you know how to draw a free body diagram, that is the first hurdle. The second hurdle is then taking that free body diagram and making a component diagram. And that has to be separate from the free body diagram. So free body diagrams can be worth anywhere from 2 points all the way up to maybe 3 or 4. Probably in the range of 3 is what we typically see. To get all those points, you only can put forces. You can't put components. So we always talk about drawing 2 dots. One dot, and that dot is for the free body diagram. The second dot is for the FBD, the free body diagram, and that is with components. Okay, so got to be careful that you're doing that. If you have those 2 things right, you're on your way. So it's super easy to do, but you got to make sure that you're practicing those. Go back, review those, make sure you can do them, and you can do them in your sleep. You can wake up and do one in the middle of the night, boom, like that. Not that I'm encouraging you to set your alarm at 2 in the morning and get up and do 5 free body diagrams when you're super tired to see how well you do, but that would be a good idea, I guess, if you like that type of thing. But if you don't do that. But get up in the morning, do a couple before you go to bed, do a couple, make sure you have the answer keys. That is just way too important for this. If you remember, it was the most important thing that you need to know. You must also then know how to find the sum of the forces. So sometimes teachers will do sum of the forces like this. We use the Greek letter sigma, and that sigma just means sum. So we're doing the sum of, or F net. And you'll notice that on the AP Physics 1 equation sheet, it's written both ways. They either say A, so the acceleration of a system is equal to the sum of the forces of that system divided by the mass of the system, or it's equal to the net force. And we take that net force and divide it by the mass of the system. So we're trying to find the acceleration of the system. So let's go ahead. We're going to practice a little bit. So I'd like for you to do is grab a piece of paper, grab a pencil. You could write this if you're really good. You have your own set of dry erase markers, and you have little boards that you can write on, or the kitchen table, as long as it's a marker that you can see it on. Should erase. I would test it before you do anything kind of crazy like that. We're going to draw a free body diagram for an object and an incline. And this one has friction. Now, I want to draw the free body diagram 3 different ways, okay? The first one we're going to draw over here on a dot. Then we're going to actually draw it on the actual box itself. And then over here, we're going to draw the component diagram. So this is a dotted free body diagram. This is going to be a free body diagram on a box, okay? So I'm going to just call it on a box, because sometimes they have you do that. You're going to see how it's different. And then here we're going to do the free body diagram with our components. So it's really important that you are able to do it all 3 ways, because you're going to be required to at least do the free body diagram on the dot. You then will also have to do the component diagram for yourself. They don't ever grade that, so we don't look at this one. We only look at the free body diagram. But then when you do the sum of the forces, you have to have this and have it right. And then the last thing we're going to always want to make sure that we know how to do is to do it on an actual box, because on a box is way different than doing it on a dot, because we've got a few more places that you can do things. So I just picked up my eraser because I want to get rid of where it says FBD on the box, because we're going to actually draw some stuff that's going to be right on top of that. So this is something we haven't done in class a lot, but I think it needs to be covered more by all the teachers, but it's just really hard to fit it in. So if we're doing a free body diagram, let's do it on the box first, because I think this is the one that is the hardest to get all the points on. If you do it on the box, we always say, well, where is all the mass of the box located? And it's at the center of the box. So that's the center of mass. For a circle, it'd be in the middle of the circle. If it's an oval, it'd be in the middle of the oval. So any object, if you can find that center, that's where we start. So we're going to draw a line straight down. That line, remember, is going to be mg. So that's super easy. The second line that we're going to draw on this is the normal force. The normal force, remember, is always at 90 degrees from the surface. I'm not going to draw that 90-degree box there, though, because that would be extra lines and we would have to take points off. So don't draw that. Instead, just draw the arrow, but notice that it starts at the surface and not at the middle. The only one that starts at the middle, and this one should be straight, and I don't know why I can't draw a straight line, starts at the middle of the box. This one starts where the two surfaces connect. And if you remember, the force of friction is equal to mu times the normal force. And because of that, we know that the force of friction needs to start where the normal force does, and that's right on the surface. So this one is going to be the force of friction. Now, because it's not moving, we're going to call this the force of static friction. So we're going to maybe even put the FS here. It's not necessary. You can just call it the force of friction. The free body diagram on a dot is going to be very similar, but we have one glaring difference. And that glaring difference is everything will start on the dot, including the force of friction and the normal force. Whereas if we were doing it for a box like this, instead of just a point, then you'd have to start one thing in the middle and the other two things on the surface. So this is now the normal force. All right, cool. I've got to do all the components now. So whenever you do a component diagram, I would draw the surface. So I would draw a line that shows the surface. Notice we did not draw the line for the surface here. Why? Well, it's because if you draw anything extra on the free body diagram, they'll take points off. And typically, they will give you the surface to draw this on anyway, so you don't have to worry about it. So let's draw all our lines again. Oh, that's really getting crooked, isn't it? Okay, so there's that one. Then we have the normal force, and then we have the force of friction. So off to the side, I would draw a coordinate axis. This just shows what's positive. So this is positive perpendicular to the surface. This one is positive parallel to the surface. The only arrows that I can leave alone, the ones that I can't do anything with, are the ones that are in these directions. So either up and down perpendicular, or up and down, or left and right, I guess you could say parallel. This one is up and down, I can't touch it. This one is okay, I can't touch it. So something needs to happen with this one. Remember, your angle is right here. Where do we put the angle now when we draw the perpendicular and the parallel components? So here's your first interactive part. I want you to tell me, where should I put the angle? What is the reference point that tells me where that angle goes? So I'll give you a second to maybe tell me where you think that the angle will go inside of the triangle. Yeah, so I'm seeing some answers, and that is perfect. You guys have it. It is next to the dot. So we are going to put that angle right here. It has to be next to the dot. If you put it down on the bottom, that is not the same angle. You would have to take 90 minus the angle to get it down here. So please don't put it down there. Instead, we want it right here, right next to the dot. You could even, if you want to, draw a dot here so that you can see if you just take this and rotate it. So let me show you down here. Here I've got a dot. Here I've got my line. If I take this and I rotate it this direction, so I turn it so that it goes 90 degrees, I would now have the following. I would have this. I just thought about that. Isn't that cool? So when I rotate it, that angle is also 90 degrees. You learn something new every time, I guess. So if I rotate it 90 degrees to the right, so I'm going to go 90 degrees, notice that it looks just like this. Cool. So that's something I think might help a lot of you that aren't sure where to put it. Make sure that you remember that, because that would be something really cool, especially in class. If your teacher tomorrow, you might want to mention to him that this is a really way to find out where that angle is. You could also do it the opposite way if you're going the opposite way. So now that we have these, let's go ahead and label all these Fn. We know that this is the force of friction. We know that this is mg down. So now I've got to figure out, what is this side? So it's mg times something times the angle. And then we have the one that's right here, and it is mg times something times the angle. So help me out here. This is the opposite side. Do I want sine or cosine? So either type an S or a C, and I'm starting to see it already. Very good. Sine. So this one is definitely the opposite side. So it is the sine of the angle. Excellent job. If that's the sine, this one's got to be the cosine of the angle. So we'll put that guy in right there. Now I have everything I need for the free body diagram for an object on an incline with friction. We have our free body diagram. This would typically be 3 points, one for Fn, one for Ff, and one for Mg. On this one, they would also do 3 points, but you have to start the Fn and the Ff from the surface and the Mg from the middle. So just be really careful with that. Alrighty, let's go ahead and take a look at this one. Ah, yes, it is the Atwood's machine. And for this one, there are no components. Why? Because everything is going to be up and down. So we're going to draw a left dot. We're going to call this one mass 1. And over here, we're going to call this one mass 2. I wouldn't write anything next to the dots on an actual free body diagram. But what I would do is when you draw your masses, you want to put M1G. So this is mass 1, so we're going to put M1G. And then it looks like mass 2 is probably heavier. We're going to say it is. And because it is, this line needs to be longer than the other one. So this one is M2G. Now we have one string. And if I have one string, am I going to have two different tensions? Or will I have the same tension in both of these? And excellent. People are now kind of answering, and you guys are doing an awesome job. Very good. It should be the same. Very good. Excellent job. So these are the same. So this one is going to be, we're going to call it this long. So we're going to call it the force of tension. And then we have this one. I'm so proud of you guys. That was awesome. So force of tension. And that's it. So drawing a free body diagram for an Atwood's machine is super easy. So you always pray right before the test, please, AP people, give me an Atwood's machine, because it's simple, easy to do. Let's go ahead and go on to the next one. The next one, oh, here we've got a free body diagram for a horizontal Atwood's machine. And this one is also with friction. Now the friction is not going to be with the hanging mass. Instead, it's going to be with the mass here. They're not labeled. If they ever do this to you, go ahead and put in M1 and put in your own M2. Super important to do. And that would really help. Okay, so here we go. Let's go ahead and we'll put a dot here for M1, and we're going to put another dot over here for M2. If you want to, you could put one up higher and one down lower, but you really don't have to do that. So let's think about all of the forces for M1. Tell me how many forces are acting on M1 in this situation. You can either type a 1, a 2, a 3, a 4, or a 5. So don't go any more than that. So how many total forces are acting on M1? I'm seeing a lot of different answers. I'm seeing both 3 and 4. So it would be 3, but only if there's no friction. Unfortunately, this one does have friction. So this one's actually going to be 4 forces. So let's go through all 4 of those forces. First force, straight down, is always M1G or M2G or just Mg. Straight up is going to be the normal force for this block. So we're going to call it Fn, and it's the only normal force, so we won't number it. To the right, we have tension, so that's Ft, but remember this one has friction. And because the block will be moving to the right, and it doesn't have wheels and it can't power itself, then the friction, so since this is positive velocity, our friction has got to be going in the opposite direction. So that's our force of friction. So here we're going to move this, and it goes back, and it is the force of friction. So force of tension and force of friction. When we think about this box, remember up, so we're going to say it's moving in this direction, that's positive. So this box is going to move down, and that's positive. Up here is tension. We know down is going to be the weight, but when we draw it over here, we want to make sure that we mark up as Ft, and then when we mark down, we got to remember this one is M2G, okay? Yes, cool, that'll work. So that's the difference, and that's kind of what you want to see. Let's go ahead, and now what we're going to do is we're going to take a look at a couple of different AP problems. So if you had time and you got on a little bit early, you were able to see that you could have printed these if you wanted to. If you didn't print them, you can do these on a separate sheet of paper. Just kind of put it on the side, and you can do that. So here's what we're looking at. So we have a 0.4 kilogram object. It's moving in a straight line under the action of a net force. Well, give me a good example of that. So that might be, I've got a person, and that person is pushing a shopping cart. Okay, so here's the infamous shopping cart. And when they push that shopping cart, they're pushing it in a straight line, and they are using a force to push it with. Okay. The graph up here shows velocity. So anytime you see a graph, circle what's there. I know that seems really weird, but that will help you so that you don't think that this is position versus time, because that's so much different, so much different. The graph does show velocity as a function of time during that 25-second interval. So at time 0, the object is at a position of 0. So we know we're starting right at the beginning. On the grid below, they want us to sketch the acceleration as a function of time. So this is something that we did in kinematics, but this is actually a force problem. You're going to find out why here in just a second. When we do it, we also have to label our scale. So we want to make sure that we fill up as much of this as humanly possible. Out of the three, A, B, and C, which one has the largest magnitude of acceleration? Which one would have the biggest acceleration, whether it is positive or negative? And you guys are on it. I'm seeing a lot of the same answer. And that answer that I'm seeing is letter A. So that's beautiful. So good job, guys. Letter A is going to have the biggest acceleration. So it's going to be the one that we can say is going to set our scale. If I want to find the acceleration at letter A, what do I have to find about this line? So what do I need to find about the line? Excellent. So our first person has said slope. Now everybody else is saying slope. Very good. So let's find the slope of this. We know that the slope of the line will be acceleration. Why is that? Because that is the change in velocity divided by the change in time. Our change in velocity, we go up 10. We're going to go over 5. So what is our acceleration? What is our magnitude? So positive, negative, and then tell me what the number is. Very good. So I'm starting to see it. It is positive 2. Remember, the unit here is a meter per second squared, and they did give that to you, which is a hint. So that should help you see that it is the slope. So our acceleration from 0 to 5 seconds is positive 2. That is, it looks like, the biggest. So we notice that there are 1, 2, 3, 4, 5, 6, 7, 8 lines here. So let's go 1, 2, 3, 4, and we're going to put in a number 1. And then we're going to go up 1, 2, 3, 4 more, and we're going to put in a number 2. Because we know that our maximum acceleration is going to be no bigger than 2. And that's because this one has that maximum acceleration. Because this one's 2, and let's make this number 1 since I underlined here. We're going to start here. How far do I go over? Do I go over to the 5, 10, 15, 20, or 25 when I do this? How far should I go when I do this? Should I go just 5 seconds, 10 seconds, 15, 20, or 25 seconds? Yeah, so notice that this only does this for this first 5 seconds. So we're going to go over 5 seconds. Remember, acceleration versus time should always be a horizontal line, and unless something really weird is happening, like there is something getting jerked. If that's true, then this will not be a flat line. But for almost all, probably 99% of AP Physics 1 questions, this will be a straight line. How about letter B? What would be my slope for letter B? So I don't have any rise, and I don't have any fall. So this is definitely, like you guys are saying already, it's 0. I would not draw a line that connects them. It might be mistaken for your changing your acceleration over the entire 5-second period of time, okay? So at 5 seconds, you have all those accelerations. Instead, I would just draw a flat line that goes straight across. How about for letter C? So for letter C, now we have an issue. Why do we have an issue? What is the problem with letter C? Well, for letter C, it is negative. So we can't make this one and this too. So remember, if you mess up on the AP test, you can do one of two things. You can either scratch stuff out and they'll ignore it, or you can use your eraser. I'm just going to scratch it out. So what am I going to do? I'm going to scratch it out, but I'm going to call this 0. Then I'm going to go up 2 lines. I'm going to call this +1. I'm going to go down 2 lines, call this -1, and down 2 more and call it -2. At this point, I need to scratch out what I did here or erase it. And then I'm going to redraw what I did right on this middle line. So that is how you correct your mistakes without spending a ton of time doing it on the AP test. Notice all we did was we scratched this out and we scratched this out. Now we're set. So everything still looks pretty good. We're going to fall a unit of 5. And we do that over a time period of 10. So this is going to be 5 divided by 10. And notice that we lost 5. So this is going to be -5 over 10, which is -0.5. So we are going to have an acceleration of -0.5 that's going to go from here to here. Okay. So when you actually do this on the AP test, or if it's on a test that you take in class, you would definitely want to do it a lot quicker than what we've done it here, because remember, you're on a time crunch. So this one probably should have taken you maybe a minute, maybe 2 at the most. But we talked through it, so you kind of saw what happened. So let's go ahead and take a look at the next part. It says calculate the position of the object at t equals 5. So they want us to calculate the position of the object at t is equal to 5. So let's think about what we know. We know that our time is, elapsed time is 5 seconds. We know that our final velocity is equal to 10 meters per second. We also know that our original velocity is equal to 0. So sorry, meters per second. We also know that our acceleration is equal to, and here we said it was 10 divided by 5, so that's +2 meters per second squared. So we can do this a couple of different ways if we want to know the position. We could say that the final velocity squared is equal to the original velocity, original velocity squared plus 2 times the acceleration times that change in position. Since we started at 0, that would give us the final. We could also say the final velocity is equal to the original velocity plus acceleration times time. So either way, you can do this. Notice though that this one, it does not give you the change in position. So you can't do it that way. However, you could use our equation delta x is equal to the original velocity times time plus 1/2 of a t squared. So either way you do it, you're going to get exactly the same answer. Our final velocity is 10, so this would be 100. That'd be equal to 0 plus 2 times our acceleration, which is 2, and times delta x. So 2 times 2 is 4. 100 divided by 4 would give me a change in position equal to 25 meters. If for some reason you did it this way, we could do the same thing. This is 0 plus 1/2 of a, and remember a is 2, and our time here was 5. So 5 times, so 5 squared is 25. These cancel out and you get exactly the same answer. So typically on most AP tests, there's more than one way to do a problem. So we have all those ways as we read your tests and score them, you do that. Yes, 100%, you will always have an entire equation sheet on both the multiple choice and on the free response. So on both the multiple choice, I got a little bit of lag here, and on the FRQ. So hopefully that lag doesn't last too long here. So you get a little bit on both. Yeah, there we go. It's much better. So multiple choice and the free response questions, you will get the equation. So don't worry about that at all. All right, here we go. On which segment of the graph is the net force acting on the object 0? Is it A, B, or C? So I will have you vote. You can vote A, you can vote B, or you can vote C. Totally up to you. A, B, or C. So we're looking for the net force. We want it to be 0. Yeah, so lots of B's. That would be the correct answer. Now we've got to justify our answer. So this is our answer. Remember, anytime you answer something and it says justify, we want to use A, B, C, D. We want to answer the question, which we did. We checked B. We want basic physics. So the basic physics that we're going to use here is we're just going to say acceleration is the slope of the velocity versus time graph. We're going to cite our evidence. So we're going to say from 5 to 10, well, actually 5 to 15 seconds, the slope is 0. The other thing we can put in basic physics is F. So the sum of the forces of the net force is equal to M times A. Now we can draw it together and we can say since acceleration is equal to 0 and F, sum of the forces, is equal to MA, our net force is 0 from 5 to 10 seconds. This is the best way to answer these justify your answer questions. I know that a lot of people do this for paragraph length response. It's the same thing. If you justify your answer and you do it in this fashion, there is no way, unless you don't know what you're doing, there's no way that you're going to miss points. So if you do this, you've really explained it very well, but you've been very concise and very to the point. So that's probably one of the best, if not the best way of doing it. Let's go ahead and take a look at the next part. This is letter D. It says calculate the net force on the object during the first 3 seconds of motion. Now, they try to throw you by telling you 3 seconds. And so you're struggling because you're going, well, half of this is 2.5. So that'd be right at this point. Yeah, but right at that point, right at this point, it wouldn't matter. The net force is going to be the same along this whole line. Why is that? Well, it's because the sum of the forces are equal to the mass of the object times its acceleration. And it has the same acceleration from 0 to 5. So they could have said 1.352 seconds. They could have also said 4.999 seconds. It would have all been the same. They just chose 3 arbitrarily to try to throw you a little bit. We know that the acceleration here, and it says calculate, so we need an equation, which we have. We know the mass is 0.4. We know the acceleration is 2. And so now to find that net force, we just take 0.4 times 2, which is 0.4 times 2, which is 0.8 meters. I'm sorry, 0.8 newtons. So that is our net force. So 0.4 times 2 is going to be 0.8 newtons. Okay, super easy problem to do. Next thing, this is the next problem. So this is the last problem that we're going to do as we go through. We do have a question, so let's pause for a second and see if we can answer the question. Oh, cool. So could you find area under the VT graph? If you find the area, so let's go back because that's an awesome question. So thank you very much, Austin. That's an awesome question. If I want to know how far this goes, see, you guys are thinking, that's beautiful. If I want to know how far it goes, okay, I could find the area under the VT graph. So I want to calculate the position. I want to find the area. So here I have a triangle. And that triangle, the area is equal to 1/2 of the base times the height. So that would be 1/2 of the time, okay, right? So 1/2 of the base would be 1/2 of the time times our velocity. If you do that, you're going to end up with 1/2 of 5 times 10. 5 times 10 is 50. If you divide it by 2, you do get the area, which is also the same as the change in position. So that is 25 meters. That would be the short and simple way to do it. So excellent, excellent job. I really appreciate that. Thank you so much for asking that question. So hopefully that answered, and we have answered that question. So if you have more questions, feel free to go down and use the ask a question down at the bottom about any of these questions. Cool. All right, so let's move on to the next one. So pretty easy problem. All we had to do there was go through, kind of think about force, how it relates to the graphs of kinematics. That ties 2 things together. You're going to notice that the problems on the AP test will always have multiple parts, and they will always cover more than one topic. So this one did kinematics and it does dynamics. So it's taken the two things we've learned so far and put them together. Alrighty, so here we go again. It says a box is being pushed at a constant speed up an incline plane to a vertical height of 3 meters above the ground. So this person is pushing the box from the bottom all the way up to the top. Notice that the height change here is exactly 3 meters. The mass of the box is 50 kilograms. So one of the things I like to do is put the mass in kilograms inside the box. Remember, everything needs to be in kilograms, meters, and seconds. We always say that you are kissing my bass, so that's a fish. And so that would be kg, m, and s. And so that makes it a lot easier to remember what the units need to be. So whenever I go fishing, that's what I like to do. And the coefficient of friction, mu k, mu k, is that static or is that sliding friction? Somebody help me out here. Is that static friction or sliding? Yes. So I have lots of people now say sliding. Very good. So it doesn't mean that it's got wheels and that it's moving. It's just sliding. That's what we want. And that mu value is 0.3. So mu k is equal to 0.3. Mu k is equal to 0.3. There are no units for mu. So remember that too. That's really important. On the dot below that represents the box, so we don't have to draw it on the box, which makes it a lot easier. Draw and label the forces, not the components acting on the box. Is there friction? Yes. How do we know? Because it says there is a coefficient of friction. So if you're ever confused and they don't tell you whether there's friction or not, look really hard because sometimes it's hidden there. Straight down, we know that this arrow is going to be mg. We know that we have, oops, that's not exactly what we want. So let's back that one off here. Well, it's close enough. So we do want, so here we want a line going perpendicular. So we know that this is the normal force. Yes, Kendall, sliding is the same as kinetic. So kinetic friction is equal to sliding friction. If you're pulling a wagon, that wagon wheel, they don't slide. Instead, these make contact with the ground at one point and then it rolls on. So that's actually not kinetic friction. That would be static friction. So kinetic and sliding are the same. S, if I have friction that's static, it's Fs, and that means static, not moving. Okay, so just the difference between the two. And then my question is, which way is friction? If this person is pushing the box up the incline, is friction going up the incline or is it going down the incline? So I'm seeing a lot of people already, and they are saying down the incline. So that would be correct. So this is the force of friction. We do have one more force. What is the last force? What is the last force that we need to put on here? Good. So you can name this a lot of different things. One of them would be an applied force. You could also write FP for the force of a push or even right push. So that's totally up to you. So F push, F app, however you want to do it, that would work out. Now, if they were pulling it up the hill, you'd probably want to say FT for force of tension. But because they're pushing it, we're going to call it F push or F applied, APP. That would be our free body diagram. They would probably give you 3 points maybe for this. They would give you 1 point for having these two being equal and opposite, 1 point for the normal force being 90 degrees, and 1 point for mg pointing straight down. On a good day, they would give you 4, but it's usually not a good day when you take the AP test. It's a fun day, but it's not a great day because you're tired when you get done. They want us to draw and label all the components acting on this box. So now we're going to do the same thing we had before, but this time we need to draw all of our components. So this is Fn. We have going in this direction. This is the force of friction. Why? Because we are moving in this direction, and that is the force of the push. So because we're moving up the incline, we know that this is going to be positive, and we know that straight up is going to be positive. This is positive perpendicular to the incline. This is positive parallel. So I want to draw now I've got my angle right here. Remember, I can do all this on this diagram because this is my component diagram and not my free body diagram. If I have my angle here, I could put a line like this and then come over, but I don't want to do that. Remember, we start at the dot, and we never want to have anything along the incline. We want to have it parallel and perpendicular to the incline, but I don't want to draw it over here and here. And that's mainly because you're going to have a force there. It's always confusing. So be really careful that you don't do that. Right here is our angle theta. And so this side is going to be mg times the cosine of the angle. And the bottom here is going to be mg sine of the angle. Okay, so now we have our free body diagram. We've labeled and we have all of our forces. We know that going up the incline is positive. It's positive parallel, and we know that going straight up and down into or out of or off of that incline would be positive perpendicular. So it's important that you, on your component diagram, draw this because it'll help you when you do the next step. So what's the next step? Typically, the next step in these is to derive some sort of equation. Remember, derive means more than just write the answer. So you actually have to put everything in. So I'm going to quickly go through. I'm going to put all my components back. So we said this is mg, sine of the angle. This one is mg cosine of the angle. So there's our angle. We know that this is Fn, and we know that down the hill is friction, and we know up the hill is the force of the push. So they want us to find the normal force. Normal force is the sum of the forces in the perpendicular. So that would be this way. And that should be equal to 0 because it's not accelerating up or down the hill. And by up or down, I guess I mean perpendicular to the hill. Because it's not accelerating, we know that up is positive, so that would be Fn. Down the hill is going to be mg cosine of the angle. So I guess when I say down, I'm sorry, I mean down to the left. So Fn minus mg cosine of the angle is equal to 0. And so now Fn is equal to mg cosine of the angle. So we've done that a million times. I'm sure your teachers had you do this a bunch as you go through. So that one is deriving the normal force. All right, we do have a couple more questions. So before we go on, let's go ahead and check our questions. Should the applied force and the force of friction be on the dotted line or just above it? Oh, great question, Aiden. So that one, it should be on the dotted line. I'm drawing it just slightly above so you can see it, but you see that I did the force of friction, and that one is actually on the dotted line where it belongs. It's just really hard to try to draw this on the screen. So use your ruler. That's the best thing to do. Just make sure you're drawing them right on there. Isn't the applied force basically Fn? Sure. You could think of it that way because they are touching. But for this one, we're going to distinguish it from the Fn that is going this direction by saying that this push here, even though it is normal force, let's call it Fp only because it will distinguish it when we do this type of math. So that's a great question, Joe. Hopefully that question and my answer maybe makes sense. If not, let me know, and we can go back through and do it again. We got another question that says, when drawing a free body diagram in this situation, would you need to make the F up arrow longer than the FF since it's moving? Great question. You do not need to make it a longer arrow. Here's why. If it's moving with a constant velocity, so if our velocity is constant, that means that acceleration would be equal to 0. If there's no acceleration, the two forces have to be equal and opposite. And that's why. So you don't have to do that. If it said that it's accelerating up the hill, then you would. But in this case, we wouldn't have to do that. You could just do the other. So hopefully that helps, and you've been able to see that. So great questions. Keep asking questions down at the bottom. That makes me better at what I do because I see the questions I don't think of anymore. But you remind me of all those great questions. So good job. The next thing they want us to do is calculate the normal force on the plane of the box. So last time we said that the normal force was equal to mg times the cosine of the angle. Our angle is 20 degrees, so we're going to say cosine of 20 degrees. And then our mass here is of the box, which is 50. And we're going to multiply that times 10 since it's g. So it'd be 500 times the cosine of 20. So 500 times the cosine of 20 gives me 470, somewhere around there. So our normal force is less. Your normal force on an incline should always be less than your mg. So my mg here is 500, and we said that the normal force is 469.8. So if you want to be technical, there we go. And that would be newtons, and this is newtons. So they are not the same. So 469 or 470 newtons. Okay, so now we've calculated it. Next thing they want us to do is we've calculated the normal force. They want us to find a formula for the force of gravity acting on the box that is parallel to the plane. So basically all we're doing here is we've got mg, and they want one that is parallel. So that would be this side. We already said that this side is mg times the sine of the angle. So this would be the force of gravity acting on the box parallel. So if you wanted to write an equation, you could say force of gravity parallel to the plane would be equal to mg sine of the angle. They're really just asking what is the component of the force that is parallel to the plane. So that's all it was. That's your formula. The next thing they're going to do is they're going to ask you to solve for that. So let's do that. We want the force of gravity that is parallel to the plane. That is mg sine of the angle. We did cosine of the angle in the last one because it was perpendicular, if you remember. And that's the same as the normal force. So now we're going to take 50 times 10, and we're going to do the sine of 20 this time. So let's see what that is. 500 times the sine of 20 is going to give us 171. So 171 newtons. So most people then ask, well, can I just take that 171 and add it to the 469.8? No, you can't do that. Obviously, it doesn't end up being 500. You could use the Pythagorean theorem to add the two. Why could you do that? So remember, mg pointing down here is the hypotenuse. The one that was the cosine of the angle is the longer of the two sides, but it's shorter than the hypotenuse, and then my opposite side would be the 171. So now if we use the Pythagorean theorem, you should get 500 when you add those together. So just a tidbit for us. They want us to find an equation for the friction force between the plane and the box. So remember, the friction force is going in this direction. So this is the force of friction. And to find that, we have to find out what are the sum of the forces that are acting parallel. So we have that force. We do have the force of the push. And then remember, we also have this one component right here, which was mg times the sine of the angle, which is theta. Let's just call it theta. That'd be easy. Okay, we said up the hill is positive. So this is going to be some of the forces in the parallel direction are equal to, and because this says constant speed, somebody had asked about the acceleration earlier, it is moving at a constant speed. We know the sum of the forces parallel are equal to 0. How many forces do we have that are parallel to the, I'm going to ask you a question in a while, so let's just see how many of you are still awake. How many forces are parallel to the plane? How many? Very good. Zach is on it. Beautiful. Good job. So you guys are all still awake. That's awesome. So there are 3. We have force of the push, which is positive. Mg sine of the angle, notice that it is to the right of the dot. If it's to the right of the dot, it's negative. So that's minus mg sine of the angle minus the force of friction. And that is equal to 0. Okay. The next thing that they want us to do here is they want us to find the friction force between the plane and the box. So if we use the equation that we have here, we're going to say the force of friction is equal to the force of the push. Okay, so force of friction is going to go on this side. It's the force of the push minus mg sine of the angle. The problem we have is we don't know the force of the push. Okay, but they did tell us something kind of interesting. They told us mu k. So instead of using the equation we have here, remember there's another equation for the force of friction that is on your equation sheet. That force of friction is equal to mu k times the normal force. Well, we already said what the normal force was, and we know what mu k is. So mu k is 0.3. If we go back a couple slides, we'll see what the normal force is. We know the normal force is 469.8. So for this one, we're going to put in 469.8. So 0.3 times our normal force will be equal to the force of friction. So I'm going to go ahead and do that. 0.3 times 469.8 gives me 141 or 149.4, but let's just do 141 newtons. So there is our force of friction. We have an equation. We now have solved it. I know that we did it kind of in the wrong spot. That's okay. The next thing they want us to do is find the force applied by the person on the box. Well, we've really already started that. To find the force of the person, notice we can still use this equation. So let's use it. We'll write the answer down here. The force of the person would be equal to, going to move the force of friction over, add it, move the mg sine of the angle over, so we add it. So the force of the person has to be equal to both the gravity component going down as well as the friction that is acting in the opposite direction. We know friction is 141. We know mg sine is 171. So we're going to take 141. So we're going to calculate it now. We're going to take 141, which is the force of friction, plus 171, which was mg sine of the angle. And we're going to add those together, and those should be equal to the force of the push. Now, where did we get that? Let's back up one more time. Here we said sum of the forces parallel. Those are the three forces. So even though this one's down here, it's still part of our system. Fp minus mg sine of the angle minus the force of friction. So Fp is mg sine of the angle plus the force of friction. So when we come back over, we've got those two things, 141 plus 171. And if we add those two together, 1 and 1 is 2, 7 and 4 is 11, and 1 and 1 is 2, so it'd be 212 newtons. That is what that force of the person needs to be to push that box down the hill. Alrighty, so that is all I've got. I do have, though, a question. So let's answer a question, then we'll take as many questions as we can do it again. So you said, do you mind explaining E again? No, I don't mind at all, and I will be glad to do that. Oh, somebody just said it's 312. You are absolutely right. Thanks, Zach. That is actually 312. My bad. Thanks, guys, for checking my math. It's late. It's past my bedtime. 312 newtons. So, Zach, excellent job. I'll bring you a candy bar tomorrow, a little candy bar. Not a big one, but a little one. So that is 312. Somebody wanted me to go through E again, so I'd be glad to do that. Let's go back to E. They want us to find a formula for the force of gravity acting on the box that is parallel to the plane. So here's our plane. We know this is the force due to gravity, but it has two components. It has a force of gravity component that is perpendicular to the plane. So that's this one, because that makes a 90-degree angle. And then a 180-degree angle would be this side. And that, remember, we said is mg sine of the angle. So Fg here is really mg times the cosine of the angle. And Fg that's parallel, so the force of gravity parallel, which is mg parallel, which we're going to call mg sine of the angle, is this side. So hopefully that helps a little bit, and you've seen that one. If you have any other questions, if you don't mind typing them in that box, that would be awesome, because I'll see them and I'm able to go in and kind of record those questions, and we can help you out. Anybody else have any other questions on these two problems that could eventually be on a test that you might see? Who knows? You know what I mean? But I think that's all I've got.